Many times in life we want to compare two things and not just do a hypothesis test testing one proportion. It's more likely we're going to be comparing two things. So the key word here is two. Here's an example. Remember doing these? We would randomly assign half of our subjects to a treatment group. Let's say we're testing to see whether a drug, a pain relief drug, works well, and then the other half, let's say, would get a placebo. And we would double blind it so people didn't know which group they were in. And we would run the experiment, and we would take the data and compare groups. This is where we are right now. We're learning to take the data and see if there's a significant difference between the two. And if there is a significant difference, and if it's a well-designed experiment, we can claim causation and actually learn something, and find strong evidence for or against something, like whether a drug works or whether two groups are different. Groups have to be independent of each other, but if we ran two different groups of people, that's generally the case. So our null hypothesis, we're still doing this, we're just tweaking things a little bit, going to be hearing whether P is equal to a certain proportion to see if the two proportions are different or not. All hypothesis always starts there's no means no difference. So we're going to assume that there's no difference in two groups. Let's bring in a different example. We're trying to find out whether males or teens are more likely to get into an accident driving, who are the better or worse drivers. So let's say that we're comparing those two population proportions. Now we can't collect all the data in the samples. We're going to compare and see which males or females accidents and really different. But the weird thing here is, because the null assumes proportions are equivalent, that there's no difference in their driving skills, then actually these two are all from the same pool of individuals, we're saying. So we call, again, that's because we assume that there's no difference. So we have two proportions are coming from one of individuals, and we have to use this pooled sample proportion. We're drawing from one population. So we would have to calculate a pooled p hat, and that's just taking your 2x number of accidents for males plus number of males divided by the total sample size added up. We use that pooled sample proportion in our standard deviation. So the standard deviation formula got a little longer, but it's still, we're going to take hat q hat over n1 q hat over n2 under a big square root. And then our z-score is really no different. We're going to compare the proportion of males that got in an accident to the females. See how much different they are divided by our standard deviation. When is it reliable? We've got to keep checking conditions. What assumptions do we have to make? Well, they're the same for the most part. We have to have a simple random sample to really trust our results. Not more than 10% of the population in either case, males or females. Groups should be independent of each other. In other words, we couldn't have like twins where we had a twin boy and a twin girl in the same family and compare those two, because they're not independent. For the most part, though, if you randomly sample, you'll have an independent group of males and females. Our fourth condition, checking to see if the NPs are greater than 10, well, now we have 4 to check, and that's because we have two sample sizes, our male samples and our female samples. So we have NP hat and NQ hat, and then the female. Notice that, and I've lost my train of thought. Hang in there. that we have 4 to check. Using P, it's the pooled sample proportion. That is why we have to calculate that pooled sample to check our conditions. In a confidence interval, the changes we make are actual p hat 1 and p hat males. Because remember, we're not assuming we know proportions are equal. So all we have to work with is our sample proportion. So we would use those in our deviation. We would use, when we're calculating the interval, we would have the difference. We're finding the difference versus the females, our margin. Z of C works the same. If your confidence is 5%, your Z-score is 1.96. Conditions are the same, except for number 4, we're going to use p hat 1 and p hat 2 when we multiply and make sure they're all above 10. What can the calculator do for you? We're going to allow it to do more for us than we have been right now. But even what I'm about to show you, you still have to be able to set up all the info. That means HO and HA. You still have to check all your conditions, write them all out. You still have to write your 2-part conclusions, interpretations. But what can the calculator do for us? Let's find out here. All right, so we're going to take this data here that I made up. Let's say we got 500 random males, teenage males, and we followed them in the course of, let's say, a couple years of driving. 95 got in some type of fender bender or accident. Female data, as you can see, is right here. So we want to do a hypothesis test. Well, remember, you have to set everything up, write it all out, but our calculations can be made much easier. Check this out. We're going to go to Stat, over to Test. Now remember, this is a 2 proportion, so we're looking for 2 proportion, Z-test. Okay, calculator wants to know the information, the data, so our X1 would be 95 out of 500. Let's fix that. Our X2 would be 74 accidents, females, out of the 479 females. Notice that the sample sizes don't have to be the same amount. We can compare with different amounts. It asks then for what is your alternative hypothesis. I don't think we're going to guesstimate either way that that females or males are worse than the other. If anything, maybe males, trying to show off for the females. But we'll go with just the not equal. We'll say we don't know ahead of time which one is worse. Hit calculate and look at that. It gives you the Z-score. So you can bypass the formulas. You can bypass the standard deviation formula. It even gives us the p-value. So if these results were accurate, our Z-score is 1.47. Our p-value is right around 14%. And yes, they doubled it. Because we told them it was not equal to, the area was right around 7%. They doubled it for us, and we got 14%. So I would say that there's some evidence here that females are a little safer, but not significant enough because our p-value is 14%, and that's generally not enough to reject the null hypothesis. What if you want to know how much better females were? Because it appears that they're a little bit safer with this data. How much better? Well, let's go back to Stat, Test, and now we're looking for a confidence interval, 2 proportion that is, so 2 prop Z interval. There's a whole bunch of things we can do here. And it already has the data because I punched it in the other window. Choose the confidence level, click on Calculate, and let's see our results. Gives us the interval. Female drivers are better, we're saying. They get in how many less accidents overall? Well, between 8% less and, because this is negative, 1% more. So again, that again shows it's not significant because we have a negative and a positive. This interval is not giving us, it's giving us the difference in proportion of accidents. So females would get in anywhere between 1% and less 1% more accidents, or up to 8% and less accidents, because this is taking males minus females. All right, we'll talk more about that in class. We have a couple more pages here, though. Let's take a look. How do we talk about our conclusion? Almost the same as we've been doing, except remember we are dealing with the difference here of two proportions. So let's say that our test was between, let's go back to the drug example, the pain relief drug versus a placebo. Our null hypothesis would be that the pain relief drug is no better than a placebo. But let's assume that it should be better, so our alternative is that more people are going to experience pain relief with the drug compared to the placebo. So let's say that there were significantly more that felt better taking the drug. We would say that there is strong evidence to reject that there is no difference, which is evidence that the drug works. So we're talking about a difference here. Confidence interval is more what I'm going to talk about here, though. Let's say the confidence interval was between 9% to 17%. This is saying that between 9% and 17% more people will feel better on the drug compared to the placebo. So again, this is dealing with the difference, how many more proportion of people in the population would feel better with the drug, anywhere from 9 to 17% more than the placebo. If in a certain situation the P2 was higher, the p-hat2 was higher, you're going to get a negative interval, and that's fine. It's just saying that P1 minus P2 is a greater number, so a smaller minus a bigger number is going to give you negative numbers. So it's still saying that P2 is higher, but anywhere from 9% to 1% higher. And if you see a negative and a positive, like we did in our driving example, it's saying there's no significant difference, because one side, this is saying, could be 6% greater, or the other side could be up to 4% greater. So it's inconclusive. Don't worry about that. Ignore that right now. We're going to do that in class tomorrow. Get ready for a little quiz. See you tomorrow.